Awesome. Hi everyone. Welcome to this week's Friday presentation. Today I'm going to be presenting on something a little different and very, very interesting. It's called Generative Agents, Interactive Simulacra of Human Behavior. My name is Griffin Higgins, and my supervisors for this directed studies are obviously Prof. Ali Gurbani and Dr. Shishan Zhang. So a little bit about me. I'm a PhD student here at UMB in the Faculty of Computer Science. I'm also a cybersecurity software developer here at CIC. And I love nerdy things. We're going to be talking about something that's pretty interesting. Back when I was like a little kid, I used to play this game. It was called SimCity 4, if any of you have ever played that. So we might kind of draw some inspiration for what we're going to be talking about from that today. So some objectives. We're just going to go over the introduction of this work. We're going to go over like kind of the overview, main things of the paper, and then kind of like a pseudo demo. I wasn't going to go through everything. I didn't get as far as I wanted in the demonstration, but I'm going to cover some screenshots and just show you how far I got. So a brief aside, we might be wondering, this is a very strange title. It's talking about simulacra. What is simulacra? If you come from the social sciences, specifically sociology, you'll know that this has some very special meaning. And simulacra basically relates to things that aren't real, but that model things that are real. So there's a famous quote, and it's simulacrum is never what hides the truth. It is the truth that hides the fact that there is none. The simulacrum is true. And there's a very famous movie that has a famous book. It's called Simulacra and Simulation. So yeah, it's actually The Matrix. If you've seen that, that comes from there. And it's really important in sociology as well. But just as a quick introduction, we're going to be talking about something that's eerily similar to this thing called The Sims. And if you've ever played The Sims, we can understand that there are these kind of people that occupy this kind of world that we can kind of control. And we can also understand that they can take actions and converse with other people and go about their lives. But more specifically, if we had to define this, we would recognize that there's kind of three things. We recognize that there's agents, we'd recognize that there's an environment, and we can recognize that there's some kind of interaction that can happen. In terms of agents, these can be people, they can be animals, but they can also represent higher order things like entire organizations that can take action. We would recognize an environment, maybe like a little world, or maybe even a graph, a data structure. And then there's different kinds of interactions that can occur between the agents themselves or the environment. So what are a little bit more about agents? Agents in this setting are autonomous, like they can move on their own. They don't really need help from us or kind of scripts, if you will. They're sociable, so they can interact with other agents, presumably in a cooperative or competitive kind of setting. They're also reactive, so they can perceive and interact with the environment. And they're also proactive. They can basically make their own objectives and go about seeking their own kind of goals. They also have attributes, so they can take on kind of data, if you will. They can also have certain behaviors, they can take action, and also make decisions. This is talking about agents generally, but we might also refer to generative agents. In the past, we might think of games like Conway's Game of Life that might model agents in this kind of very rigid kind of environment. But now we're able to use large language models that can be augmented via like little databases and things like this of information that we're going to talk about today. And they can interact with their environment via text, right? They can also have some kind of reasoning capabilities, and they can be quite heterogeneous if we think about it, because we can define each of these models to be very different, if you will. And we would define all of this kind of as bounded rationality, because of course they are not real people. Of course they could not attain that same level, but we can recognize that they can be good approximations, so we would say that they're rationally bounded. We might also recognize our environment. I'm going to kind of skip through some of this. Environments can obviously have agents, and the environments can have change to them. So we can think about like the weather, for example, which can also be events that can cause changes. They can also have certain kind of properties as well. And then lastly, there's different sets of interactions that can happen in this setting. We can think about agent-to-agent interactions. We can think about environment-to-agent interactions. And we can think about agent-to-environment interactions. So now, why am I telling you all of this? This seems pretty ridiculous. Why should I care? And this isn't very important to cybersecurity, computer science, or anything we're going to be doing. I would contest this. I would say that this isn't ridiculous. I would say that this model for thinking about agent-based modeling is very good. I think we should care because there are many systems and things that kind of obey this, this structure, right? And this is important. We can think about not only like The Sims or something very similar that we're going to talk about today, but we can easily extrapolate to other circumstances, right? We could easily model a nuclear power plant. We could easily model these agents as people that work at this nuclear power plant, and we could easily model an adversary that might try to socially engineer some of those agents to simulate maybe an attack on a nuclear power plant. This is just kind of a off-the-cuff example, but my point is that we can really adapt this to our own needs, be they for good or for evil, so we should consider this respectively. So a little bit on the actual paper itself. It's super interesting, and it has a much more cheery title to it. This is a quote directly from the abstract. Generative agents wake up, cook breakfast, and head to work. Artists paint while authors write. They form opinions, notice each other, and initiate conversations. They remember and reflect on days past as they plan the next day, right? This is very different than probably how we've mostly thought about large language models and interacted with them kind of as this information retrieval system. Now we're trying to see them more as what they could be used for, which are agents to model human behavior or any other kind of behavior. So how might this actually work if we were going to make a system? Well, we might want to have some kind of agent, right? And we might want to give them like a little bit of a background. So we might make an agent and we might call them John, right? And we might say, John Lin is a pharmacy shopkeeper at the Willow Market and a pharmacy who loves to help people, and so on and so forth, right? We might describe people that John knows. We might describe what he kind of likes or other things he knows about his own life or his environment itself. So that's a little bit on how we might define one of these agents. But where will they exist? Well, we can actually place them in the context of a world or an environment along with other agents. And we can see here that they're going to kind of do this thing that's very similar to The Sims, except in this case they're going to be AI powered, or they're going to be generative agents. So how is this world made? Well, it's made with this software called Phaser, which is a web game development framework. This is more for the visualizations than anything else. But essentially there's going to be a central server that manages a JSON data structure, and it's going to keep track of all the agents' positions. It's going to keep track of all the objects, so it's going to know if the coffee machine is idle or if it's being brewed by one of the agents. And it's also going to basically establish agent-to-agent interaction capabilities, so long as the agents can actually see each other, right? They're not omniscient. They can't actually see across like the world or through walls or anything like that, just if they see other agents. But now, how is this world going to be defined, actually? How are they going to know how to traverse it, if you will? Well, we can think about the following, right? We can look and define houses. We can define rooms within houses. We can define some kind of like objects within these rooms. And we might ask, what data structure is this, right? If we're computer scientists, this might seem very familiar. This is a graph. This is a tree, right? And we can basically show them, the agents as they start to traverse this world, this graph or this tree, not in a physical sense, but just in terms of it being a structure. And that's actually one of the things I demo at the very end of my presentation. So in this world, nodes are going to represent areas or objects, right? And they could also be a kitchen or a stove. And edges between these things are going to represent containment relationships. And what we're going to do is we're going to have a large language model that will observe these edges and translate them into a form that another agent might understand. So for example, if there's an edge between a kitchen and a stove, we might say there was a stove in the kitchen that will be translated by the model. Agents also build static relationships of the environment as they observe them. So if the agent wanders off and they don't know that they left the stove on, for them the stove will always be on even if another agent comes in and turns off the stove, right? So that's something that's important to keep track of. Each agent will have their own perspective on the environment. And additionally, how we might let them move around is we're going to flatten out a portion of the agent's environment tree where it will kind of know where it is from the environment itself, where it's told. And it will be used to prompt it for where it might want to move next. So that might kind of take the following form. It might just be giving the agent all this kind of information, say, where do you want to go next, Eddie? So that's a little bit about how they're going to move around. And then we might say, well, how are they going to use objects? When an agent uses an object, the environment prompts to know what happened to it. So if the agent walks up to a coffee maker and takes some kind of action on it, the environment will say, what kind of action do you want to do on this coffee maker, right? And then the environment might change it from off to brewing, for example. So that's a little bit on the environment, how this is all going to work. But now let's talk a little bit more about the agents, because they're going to have to wake up, right? They have lives, they have to do all these kinds of things. So how are we going to plan this for them? Well, essentially, we might recognize that there's kind of a temporal dimension and a time dimension. So we might actually prompt them with their own morning routine and tell them things about their life so that they might actually go and act them out. And that might kind of take the following, where if we have this agent named Eddie, we might say, hey, Eddie, you're going to wake up and you're going to go to your college class and you're going to do all these things. We're going to prompt them with this at a very high level, just so that they have some structure, and then they're going to kind of fill in the blanks and figure out what they want to do in between. So if they need to plan a Valentine's Day party, for example, one of the things that they're going to do, they can actually fill out when they're going to do that and how the subtasks that might accompany that as well. So we might also think about the agent's memory, right? A huge concern here is the context window. LLMs are very small. Some of them are growing, but even then, we might not always want to use the entire context window. It might cause some confusion. So in the paper, they propose this memory system, essentially where agents will have memories, but these memories won't exist in their context window. They're going to exist in a little database that the agent is going to carry around with them wherever they go. That's going to be unique for each agent. And we're going to do a lot of different things. We're going to plan. We're going to reflect on memories as well, as we'll see. So this is all quite interesting. And also perceive things about the environment. So we technically refer to this database as a memory stream. So each agent is basically just going to always know a lot about the environment. So if they see the coffee makers on, that's going to be one of the entries. If they see that another agent is trying to talk to them, that's going to be another one of the entries. If we see that someone is cleaning up the kitchen, that will be another one of the entries. But then if one of the agents is prompted for something, they might have to figure out how to retrieve this information, not from their own context window, but from the database itself. So to do this, we're going to rely on three quite clever things. We're going to rely on recency. So agents should retain memories in order to make their response that are most recent in this memory stream. And we can score those, of course, easily. We can also relate the importance of a memory itself, not with respect to any other memory, but we can ask an agent, hey, you turned on the coffee maker, this was an action you wanted to do. How important is this from a scale of 1 to 10, right? Maybe the agent will assign that a value of 1 versus like an event, maybe they were in a car accident and then suddenly that's like a 10 level event for them. So it's a scale of 1 to 10. The last thing is relevance. So this one isn't done by the agent itself. Essentially, whatever the query or whatever the prompt is to the agent, they're going to take that and compare it with every other memory they have. So we would obviously do that using an embedding and using cosine similarity, just to say out of all the memories we have, what are the ones that might at least be relevant to the thing I'm trying to think about. So together, all three of these things are used to produce like a score for each memory, and the top K memories are used to actually produce the next response. So it's not the case that this is just all occurring in one greater context window. There's also this notion of reflection. So this is pretty interesting, and essentially here, we might look at all of these memories, and we might make meta memories from them. So this is done, I guess, like once every like maybe 2 or 3 hours in this game world life for each agent. So we might reflect and say, Klaus Mueller is highly dedicated to his research, and then we might form this based on maybe even another reflection that might be derived from some kind of observations that have come from the environment that the agent has observed itself. So for example, Klaus Mueller is making connections between articles might be an observation. Klaus Mueller is reading and taking notes on the articles. Klaus Mueller is reading the assigned material. So all these things might form a meta-level reflection that can also be retrieved later. So that's really interesting. So that kind of forms basically how this environment works, how agents kind of have this memory capacity so they're not just hallucinating all the time. But how are we actually going to evaluate this? Because this is kind of a strange thing to think about. How are we going to evaluate it both qualitatively and quantitatively? So the first thing that they do is something called a narrow evaluation. And I actually burst out laughing the first time I heard this because afterwards I thought, oh, of course we would do that. The researchers actually just interview each agent. They just sit them down and ask them questions. They just prompt them after everything's said and done. So for example, we might interview Claus and say, tell me about yourself, or tell me about this person that you know before the day begins. And then after we might observe them actually make contact with this person, at the end of the day, we might prompt them or interview them again in that same way to say, do you know who this person is? And if they respond that they know, that's kind of at least some evidence that they are interacting with their environment in a believable way. Because again, the agents are bounded rationally, they're not actual humans, they're just approximations. So this kind of gives us a sense of what that might be. There's also a broader evaluation for emergent behavior amongst the agent collective. So to do this, I'm going to kind of spoil it. They have two scenarios. One is somebody that's going to be running for the mayor in their little town, and then the other is somebody that throws a Valentine's Day party, which we'll see is very interesting in a moment. So in terms of the narrow evaluation in this kind of interview setting after the agents live in the world for a little while, we might ask them about themselves. We might ask give an introduction for yourself, which would be the evidence of self-knowledge. We might ask them, describe your typical weekday schedule in broad strokes. We might ask them about people they know or who's running for mayor, just general questions that relate to their memory. We might also ask them about things that relate to their planning capabilities. So what are you doing tomorrow at 10 a.m., right? And then we might also test their reactivity. So if we prompt them with some kind of event and we say, your breakfast is burning, what do you do? That would be an example of a reaction. They might turn the stove off. And then if you were to spend time with one person you met recently, who would it be and why? So this is evidence of reflections, right? We can't really pinpoint that to one single observation. That would have to come from this kind of meta observation that the agents have built in their little database that they take around with them. So in this, after they gather this, we have these kind of 5 conditions, and we use this thing called, or they use this thing called true skill rating of 100 sets of ranked data, and together this relates to the believability of the agents in the thing that they're working in, and they use human evaluators for this to make these kind of rankings. And then given a set of ranked outcomes, the true skill outputs a mean and standard deviation rating for each kind of condition that's observed. They also use statistical techniques like the Kruskal-Wallis and Dunn post hoc test, which relate to kind of statistical significant tests. And then in terms of results, the full architecture that they use is best amongst all the other conditions. So they also test ablating the agent's memory capabilities, their planning capabilities, and reflection capabilities, and they find that they perform worse in all cases. So this is just a very small snippet of that. We can see the full architecture gets the highest believability score versus with no reflection in planning, and no reflection planning and observation respectively. So that's interesting. And then I guess if we're going to assess this qualitatively without numbers, we can basically see that the agents are capable of describing themselves. They are capable of recalling and describing other agents. Their memory isn't perfect. They don't remember everything. Neither do we. So I think that's okay. And they also form incomplete memory fragments sometimes. So that might relate to the reflections of how they piece together certain observations. They tend to hallucinate embellishments to their own knowledge. It's rare for them to actually have complete hallucinations because, again, a main point is that they're not keeping all of this in a great big context window that's huge and miles long. They're keeping all of the most important information in a little database that they take around with them, and then they just one-off kind of have inference on that as they're going through. So it serves as their memory. As well as the agents, they do not claim they experienced something that they didn't, so that's good. They won't say they went to Sobeys when they didn't go, but they might add claims at the very end of things that are not exactly real. They might say that that someone else is mayor or running for mayor instead of the person that they should think that it is. So that's good to know as well, qualitatively. And in terms of the broad evaluation, here we're looking at emergent social behavior. So in the experiment, the big experiment, I guess, it was run over 2 days. They basically select one of the agents. Their name is Isabella, and they basically instruct Isabella through something called the internal voice of the agent. So it's kind of like the agent's own mind in their mind, and they say, hey, you're gonna plan a Valentine's Day party, right? Because maybe we want to see what happens. And you might say, this is kind of silly, why would we choose a Valentine's Day party? It's pretty irregular, it doesn't come up all the time. So if we see it actually come up in the experiment, it wouldn't be conflated with something like a birthday party that might reasonably just occur through random chance alone. So this is very interesting because in the experiment, they observed that the agents are actually able to diffuse information amongst the other agents, and we can kind of see this happening. So 5 more minutes, 4 more minutes, okay. So we can see Isabella, as well as all of the other agents, that they're told about the Valentine's Day party, and then, yeah. So we can see that Isabella's party diffusion increased from 4% of the agents out to 52% of the agents after a day. The agent density overall of the entire network and collective increased from about 16 to 74. So talking about the density of the graph of the networks between the agents themselves. And we can see evidence of coordination for the party. Isabella spent time inviting guests, gathering materials, enlisting help. 5 of the 12 invited agents actually showed up. So not only does this person just be instructed, and then we take our hands off the wheel, the agent now goes out, plans his Valentine's Day party, tells the other agents. The agents also have to plan and show up to the Valentine's Day party. So that's pretty remarkable that that actually happened. You might say 5 out of 12, that's not very good. 3 of the other agents had conflicts, so they knew they couldn't attend due to their planning. And then 4 out of 12 just decided not to go. They said, I don't really want to go. So it's not the case that they're just off doing something else. And this is actually the Valentine's Day party itself. It happened, so they took a little screenshot just as proof. And then in terms of boundaries and errors, the agents didn't always act believably and instead acted erratically at times. I'm kind of running out of time, so I'm gonna skip through to my questions. In terms of critical review, my questions were basically LLMs can reflect sociocultural biases in their training data. How is this considered? I don't really think it is. We don't really have as much control over the broad training data that's used to build up these language models from scratch, so that's a concern. Different languages also have different levels of semantic compression. There's an actual natural language processing term for this, I just forget off the top of my head. We can think about Latin versus English, for example, so I'd be interested to see if that makes a difference. And then I don't fully buy this idea of letting the agent decide its own priority for an event. How do we know that that number or priority they assign isn't just a hallucination? And why is there no analysis done on this? And then why have it out of 10? Why not score something from 0 to 100,000, for example? And some events from a very long time ago might also be very high priority. If I was in a car accident 5 years ago, maybe that would shape my decision making for forever on something. And then I guess I'm not fully convinced that we should only retrieve relevant similar things as the case through the cosine similarity. Technically this makes sense, so I have no objections, but often we humans assess and consider irrelevant things even subconsciously in our decision making. So that's something that is kind of neglected. And then I asked this question, and then I did catch they did very quickly talk about temperature and hyperparameters, but it'd be interesting to see what happens if you crank this all the way down or all the way up. Will the agents suddenly start just doing very unexpected things? And then why are different alpha values for all these things not used on a per agent basis to promote heterogeneity of agents? So basically, we can recall that when the agents go and retrieve all these memories, that there's different scoring techniques. So we might want to be able to crank down maybe the plan, or maybe the relevance, or maybe the recency isn't quite as important. We change that for each agent, we get them all behaving a little bit differently. Maybe we get a system that's a little more dynamic. So personal review, I guess I'm going to skip over most of these, except for the last one, which is kind of, what about adversaries? What if there was a designed rogue agent with instructions to destabilize social cohesion or disrupt cooperative goals? So what if we implemented an agent that was specifically told to go disrupt Isabella's Valentine's Day party? Would the Valentine's Day party still happen? Would it not? What would happen? And then again, I think this is very interesting. We can do a lot of different things like this. I think it gives us a rare opportunity to model social engineering attacks in kind of a sandbox environment. Obviously not to perfection, but at least have something to test out. I think that's interesting from a cybersecurity setting. And here are my references. And this was the last thing. I did make a little attempt at a demo. I wasn't going to run it here just because it's hard. But essentially, I made this little graph. And I basically had 3 agents, alpha, beta, and gamma. And they were basically told, here's where you are, here's your node number, and here are the neighbors of all the nodes that you can go to if you want. So if we zoom in on some of the agents, we can see that the beta, whenever it occupies one of the nodes that's not a node, it flips. So you can see that that's one of the agents. The other one is gamma, so it's off somewhere else. I'm pretty sure alpha, the other agent, is actually beneath beta, so they're on the same node, which is kind of interesting. And this is how they're prompted. So basically I say, your current node is 25, the neighborhood of nodes you can go to is this, and the agents that are around you in this neighborhood might be alpha. And then the agent might respond with 1, and then we might see the next, it'll just be the same thing. So we do this for the other agent as well. And the last thing is we might say this is no different than if I just created a random number generator and just let the agent just traverse through the list with just a simple Python function. This is actually not at all the same thing, because at the very end of this, I didn't get to it just because my PC was running a little hot. But we can prompt the agent and say, tell me about the graph. Tell me about the thing that you just visited. It won't know about the actual picture graph I just showed you, but it will know about everything that happens in this context window. It doesn't have a database here, but it will actually respond and say, I'm in a fully connected graph, or I'm in a graph with only 3 nodes. So we can actually ask questions about the agents, about their environment, and the agents can make decisions about where to go in their environment. So it's a very, very stripped down, simple model. I want to also consider like agent-to-agent communications. So if an agent is on the same node, maybe they can talk and do stuff. But yeah, I think I'm running out of time. So with that, I will say thank you so much for listening to my presentation.